Roscosmos recently confirmed a strategic shift that marks a significant departure from decades of international cooperation in low Earth orbit. As the International Space Station approaches its retirement, Russia has announced plans to construct the Russian Orbital Service Station, or ROS. Unlike the ISS, which orbits at an inclination of 51.6 degrees to cover most populated areas, ROS is slated for a sun-synchronous orbit at an inclination of nearly 98 degrees, passing directly over the Earth's poles. This decision reveals a fundamental divergence in engineering philosophy between the Russian space program and Western counterparts like NASA and SpaceX. To understand why this matters, we need to consider the physics that govern human spaceflight. SpaceX is currently the dominant provider of launch services to polar orbits, frequently sending Starlink and customer satellites on transporter missions using the Falcon 9. However, despite having the capability, SpaceX has never attempted to send a Crew Dragon or plan a SpaceX Starship mission for humans into these high-inclination polar trajectories. In this video, we will examine the rigorous engineering and safety constraints that make polar orbits a no-go zone for American human spaceflight. We will analyze, first, the energy tax or delta V penalty that makes launching to the poles economically inefficient for heavy platforms like SpaceX Starship. Second, the severe radiation environment found in the polar funnels of the Van Allen belts and the long-term health risks this poses to crews. And finally, the critical safety protocols regarding launch abort scenarios that effectively rule out these trajectories for NASA-certified commercial crew missions. Drawing on orbital mechanics principles, historical NASA safety data, and the current operational parameters of the SpaceX Starship program, we will uncover why Russia is building a station in an orbit that SpaceX actively avoids. To fully appreciate the engineering divergence between Russia's future plans and the current American approach led by NASA and SpaceX Starship development, we must look back at the orbital foundations laid during the post-Cold War era. For the past 2 decades, human spaceflight has been defined by the International Space Station's specific path around the Earth. The ISS orbits at an inclination of 51.6 degrees relative to the equator. This specific trajectory was not selected purely for scientific utility, but as a geopolitical compromise in the 1990s. It was the most efficient inclination that allowed the space shuttle to launch from Florida while still being accessible to Russian Soyuz rockets launching from the high-latitude Baikonur Cosmodrome in Kazakhstan. This shared orbit became the highway for human space exploration, a path now frequently traveled by SpaceX's Crew Dragon. However, the proposed Russian Orbital Service Station, or ROS, shatters this long-standing convention. Russia plans to place ROS into a sun-synchronous orbit, SSO, with an inclination of roughly 98 degrees. Unlike the ISS, which circles the globe at mid-latitudes, a spacecraft in this polar orbit flies almost directly over the North and South poles. This is not a new orbit for satellites. In fact, SpaceX regularly services this trajectory with its transporter rideshare missions, deploying commercial and government payloads that require consistent lighting conditions or global observation capabilities. However, placing a permanently crewed station in this orbit is unprecedented in the history of spaceflight. The context for this decision emerged publicly around 2021 and 2022, when Roscosmos officials, citing the aging infrastructure of the ISS, signaled their intent to withdraw from the partnership. While political tensions were a driving force, the technical justification presented was the need to monitor Russian territory in the Arctic, something the ISS's lower inclination cannot do effectively. This shift presents a stark contrast to the trajectory of the American commercial space sector. While SpaceX Starship is being developed to carry massive payloads to the Moon and Mars, its near-term human operations remain focused on equatorial and mid-latitude orbits. As we transition into the technical analysis, it becomes clear that while the technology to reach polar orbit exists, the cost, measured in both energy and human safety, is a price that NASA and SpaceX have historically been unwilling to pay for a low Earth orbit station. The first fundamental constraint that separates the American and Russian approaches to space station placement is a matter of pure physics, energy management, or what is known in aerospace engineering as the delta V budget. To understand why SpaceX Starship and NASA missions favor equatorial or mid-latitude orbits, we must look at the rotational mechanics of our planet. When a rocket launches from a facility like NASA's Kennedy Space Center in Florida, it does not simply fly upward. It flies sideways to achieve orbit. By launching toward the east, the vehicle takes advantage of Earth's rotation, which spins at approximately 900 miles per hour, 1,448 kilometers per hour at that latitude. This natural phenomenon provides a significant boost, essentially giving the rocket free velocity that reduces the amount of fuel required to reach orbit. This efficiency is a cornerstone of modern rocket technology, allowing vehicles to maximize the amount of cargo or payload they can carry. However, the physics change dramatically when targeting a polar or sun-synchronous orbit, as Russia intends for Ross. When a launch vehicle aims for the poles, it cannot utilize the Earth's rotational speed. In fact, the situation is more challenging. The rocket must expend extra energy to cancel out the existing eastward momentum before turning south or north. This maneuver imposes a severe energy tax on the launch vehicle. For a commercial operator like SpaceX, this energy penalty translates directly into lost revenue and reduced efficiency. Data from the Falcon 9 program illustrates this trade-off clearly. The payload capacity of a rocket launching to a polar trajectory is significantly lower than when launching to a standard low Earth orbit. Every pound of fuel used to change inclination is a pound of cargo that cannot be delivered. This physical reality stands in direct opposition to the design philosophy of the SpaceX Starship program. Elon Musk and his engineering team are optimizing Starship to reduce the cost per kilogram of sending mass to orbit. The goal is to make space colonization economically viable by lifting massive amounts of infrastructure as efficiently as possible. Constructing a megastructure in a polar orbit where lifting capacity is mathematically handicapped by the laws of physics violates this core tenet of efficiency. For Russia, utilizing the Vostochny Cosmodrome, this high-inclination orbit is a geographical necessity due to launch corridors that avoid dropping spent rocket stages on populated areas in China or Japan. But for the United States, which has clear access to favorable eastern trajectories over the Atlantic Ocean, choosing a polar orbit for a space station would be an unnecessary economic burden. It would require more launches to build the same size station, driving up the costs for NASA and its taxpayers without delivering a commensurate increase in scientific value for human spaceflight. Beyond the economic constraints of launch physics, a far more critical factor prevents American commercial providers from establishing a permanent presence in polar orbit: the radiological environment. To understand the severity of this challenge, we must look at the geometry of Earth's magnetosphere. Our planet is surrounded by the Van Allen radiation belts, zones of energetic charged particles trapped by Earth's magnetic field. In a standard low Earth orbit like that of the ISS, the magnetic field acts as a robust shield, deflecting the majority of harmful solar and cosmic radiation. However, at the North and South poles, these magnetic field lines curve inward toward the Earth, creating what are essentially magnetic funnels. In these polar regions, solar particles and cosmic rays can penetrate much deeper into the atmosphere. A space station in a 98-degree inclination orbit, like the proposed Ross, would pass through these high radiation zones on every single orbit, approximately 16 times per day. This exposure profile is vastly different from the recent SpaceX Starship development flights, or even the specialized SpaceX Polaris Dawn mission. While the Polaris Dawn crew flew to a high altitude of 870 miles, 1,400 kilometers, effectively passing through the inner Van Allen belt, their exposure was transient and calculated for a short duration. In contrast, Russian cosmonauts aboard Ross would be subjected to this elevated radiation environment for months at a time. From an engineering perspective, mitigating this risk requires heavy shielding. For SpaceX Starship or Crew Dragon to safely operate in such an environment for long durations, the vehicles would require additional mass for radiation protection, further reducing payload capacity. NASA adheres to the ALARA principle, keeping exposure as low as reasonably achievable. And currently, the medical consensus within the Western aerospace engineering community is that the strategic value of a polar station does not justify the increased cancer risk to the crew. Furthermore, the logistics of safety and rescue present a formidable barrier. Reaching a precise sun-synchronous orbit requires an instantaneous launch window. Unlike ISS missions, where launch teams often have minutes to accommodate minor delays, a polar launch must occur at the exact second the orbital plane aligns with the launch pad. If a sensor reading is slightly off, the scrub is immediate. More critically, we must consider the abort scenarios. When a Crew Dragon launches from Florida to the ISS, its flight path takes it over the warm waters of the Atlantic Ocean, where U.S. Navy rescue forces are staged. In a polar launch scenario, an abort during ascent could result in a capsule splashing down in the freezing, rough waters of the North Atlantic, or even near the Antarctic coast. These hostile landing zones complicate rescue operations significantly. It is highly improbable that NASA would certify a commercial crew transportation system for regular rotation missions to a destination with such high-risk abort zones. While SpaceX has mastered the art of vertical integration and rapid reuse, the safety culture ingrained in the U.S. space program prioritizes crew survivability above all else, a standard that makes a polar space station a non-starter for American operations. We have examined the divergence between Russian and American space station strategies from three distinct engineering angles: energy physics, radiation environments, and crew safety protocols. Here is what the technical analysis tells us. First, the laws of orbital mechanics impose a severe penalty on polar trajectories. The inability to utilize Earth's rotation for launch assistance creates a delta-V deficit that significantly reduces payload capacity. For a program like SpaceX Starship, which is relentlessly optimized for cost efficiency and mass to orbit, accepting this penalty for a low Earth orbit station would be economically irrational. Second, the radiological data is undeniable. Placing a human habitat in a sun-synchronous orbit exposes the crew to the unshielded funnels of the Van Allen radiation belts. While Russia is willing to accept this increased physiological risk to its cosmonauts for the sake of Arctic surveillance, NASA and Western safety standards prioritize long-term astronaut health, making such an environment unsuitable for continuous habitation. Third, the operational risks regarding launch windows and abort scenarios are too high for commercial certification. The lack of safe, accessible landing zones in the polar launch corridors creates a safety gap that current U.S. commercial crew requirements simply do not tolerate. Looking ahead, this split in philosophy signals a broader trend in space exploration. Russia is retreating to a regional focus, building a station designed to look down at its own borders. In stark contrast, the United States, through NASA and SpaceX, is looking outward. The SpaceX Starship architecture is designed not to circle the poles of Earth, but to bridge the gap to the Moon and Mars. Returning to our opening question, we now understand that Russia's decision to build Ros in a polar orbit is not a technological breakthrough, but a geographical compromise born of necessity. Conversely, SpaceX avoids this path not because they lack the rocket technology, but because their engineering calculations prove that for human colonization, the polar path is a dead end.